Hi, everybody. I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. Back on Tuesday, we talked about the contribution of wind shear to the production of severe thunderstorms and tornadoes. And then the other main contributor is something called convective available potential energy, or CAPE. There are many, many acronyms. I think I've told this story before, but I was at a luncheon at a conference back in the 80s, and the speaker said that there were too many acronyms in the world, and he wanted to start a no acronym project, or NAP, and the whole place just came down laughing. So anyway, so we're going to talk about energy and CAPE, and let's see if I can't get my little cursor to move here. We're not talking about Superman's cape. This is CAPE as it relates to meteorology. Okay, so this whole video is going to be a telestration video, and that scares me to death because I've had some problems with this in the past, but we shall see how we work here. Okay, so this is what we call a skew T chart, and basically the lines of equal temperature. Let's see if I can point these out to you here. And the reason they call it a skew T chart is that the temperature lines are skewed. So this is 10 degrees Celsius, this is 0 degrees Celsius, and so forth, minus 10, minus 20, 20, 30, and so forth. So let me get rid of that. And then all the other lines represent different things. For instance, these lines that go like this are what we call dry adiabatic lines. Now, the word adiabatic means that there's no exchange of heat from an air parcel to the environment around it. Any changes in temperature are purely due to changes in pressure, okay? But the actual amount of heat in the system remains the same. So the temperature, when the air is not saturated, declines at about the rate of 5.5 degrees per 1,000 feet. These lines here that aren't quite as steep, let me make that just a little bit thicker so you can see it. Oh, I have to do this, and then this, and then this, and then this, and I think that should work. Yes, okay. So these are the moist adiabatic lapse rates, these ones that sort of curve like this. And you'll notice as it gets colder that they're basically not that different than the dry adiabats, but that's because there's so little water in the air that it really doesn't make that much difference. What's happening, the difference between the dry and the moist lapse rate, is that once you saturate the air, then you have the release of what we call latent heat. And so that actually heats the air parcel up a little bit, and it doesn't cool as quickly as it goes up. And so when there's a lot of moisture in the air, that makes a huge difference. But when you get down into the really cold part of the environment, or this chart, then there's so little water vapor in the air that any release of latent heat is pretty insignificant, and the lapse rate tends to be pretty close to what the dry adiabatic rate is. Okay, so let's kill all of this. And what we're going to do is assume that the dew point is 68, which is 20 degrees Celsius. And we'll say that the temperature is about 95, which would be 35 degrees Celsius, okay? Now, when you take an individual air parcel, the dew point goes up along this little dotted line here called a mixing ratio line. And so it goes up like this, and the temperature of the air parcel descends along the dry adiabatic lapse rate, and so it goes up like this. Where they meet and the air becomes saturated, this is what we call the lifting condensation level, or LCL. From that point, it then descends along the moist adiabatic lapse rate, and so it begins to move along this line. Okay, so let me move that all the way up here. Okay, so this is what an actual air parcel is doing. But what is the overall environment like? Okay, so in that case, let's say they send the weather balloon up at Greensboro, and let me change colors here so you can tell the difference between the two. So the temperature at Greensboro maybe goes up like this, and this is what the weather balloon finds. Okay. Now, you can see that the air parcel, when it becomes saturated, it's warmer than the environment right in there, okay? So it's buoyant, and buoyancy is a force, which means that there's acceleration that's going to be going on with that force. So the air begins to accelerate upward along this black line, and it doesn't stop accelerating until the temperature of the air parcel equals the temperature of the environment, which would probably be up off the chart here somewhere. So this area in here between the air parcel trajectory and the I'm a terrible artist, admit that up front. Between the air parcel temperature and the environment temperature, all of this shaded area is what we call CAPE. And the larger that area is, the stronger the air accelerates upward. So when you have air that is going up a little bit here and then more here and then more here and then more here, it's being stretched, okay? And if there's any existing rotation at all in the atmosphere, and there always is at least a little, then if you stretch that, then it starts to spin faster, okay? So the more CAPE there is, the more stretching there is of the air mass, or the air parcel, if you will, and then the more rotation you end up generating. Now, that can be in the form of a rotating updraft, which would produce a severe thunderstorm, or if there's enough rotation on a really small scale and it makes it all the way down to the ground, then you've got yourself a tornado, okay? So basically what we do is that when the weather balloon goes up, and Greensboro is the closest site that does that, when it goes up, it tells us what the environment looks like, okay? And then we say, okay, what do we expect the high to be today? And what do we think the dew point's going to be in the afternoon when that high is achieved? And then we actually get a chart like this, and we say, okay, if that air gets lifted, then it's going to saturate at this level. Is it buoyant? Yes or no. And then we take it up along the moist adiabat, and we can actually calculate how much CAPE there is. And the more CAPE there is, the more acceleration there is, the more stretching there is, and the more rotation is generated. And so that's another way to generate rotation in addition to the vertical wind shear that we talked about on Tuesday. All right. I hope that makes a little bit of sense. That is bonus weather video for today. We will have another one for you coming up on Tuesday, and another daily weather update, of course, coming up on Monday afternoon. So we hope you'll join us for both of those. Hope you have a wonderful, wonderful weekend, and we'll talk to you in about 72 hours. Take care.